And each of these devices is putting out data. And even if it's putting out very little data each, the amount of data that they'll put out in total balloons very quickly, but also there's a cost for transmission of the data that people don't often think about. And in particular, if you start trying to monetize this cost, you're really talking about hundreds of billions, 10 to hundreds of billions of dollars in data transmission alone. And that's not even taking advantage of what this data is telling you. So how do we deal with this? And what is this cost leading to? The reality is that in cities worldwide, because the cost of transmission of data is so high, a lot of cities drop data. Okay, and if you look at the amount of data they're producing with all just the video cameras alone, there's about 3 terabytes of data a day that's being generated, which compares to the total amount of text data on the net, which is about 10 terabytes. So this is the total amount of text data on the net, and a third of that is being generated by video cameras on a daily basis. Consequently, because it's so expensive to transmit the data, a lot of cities drop this data. Over 90% of the data is dropped, it's lost. And it's there in other video streams as well. For instance, in high-end surgeries, which are videotaped for learning and for ensuring that things are happening properly, a lot of hospitals drop the data. And consequently, they can't really mine the information and the knowledge that's in there. So the way to really to capture this is to start pushing computing to where the data is, rather than pushing the data to where the computing is. Because I already explained that data is very expensive to transmit. So if you were to push computing to the edge, to where the data is being generated, it's likely that you will start monetizing some of the data and mining it for insights. Similarly, with unstructured data as well, the amount of data that's growing is very vast, and it's a lot of text data. There's a lot of jargon. It's very big data. There's a lot of volume. There's a lot of velocity. But primarily, even if we can deal with volume and velocity, it's the variety of data that's very hard to deal with. And so the fields of text mining and natural language processing are advancing rapidly, but they're not advancing rapidly enough. And computing isn't yet at a point where a computer can automatically understand all this data, mine it, and get insights. And so there are significant computing challenges here. And these challenges have to be overcome through advances in the algorithms, as well as in the understanding of the data itself in a much deeper fashion. And I'm going to skip over this section. I don't want to spend too much time here, but primarily what this talks about is that there's a cycle between sensing what the data is, learning the data, and acting in order to monetize and to take advantage of all this insight. And there are a lot of issues here with respect to how much sensor coverage do you need to have, both in physical sensing and natural sensing. How much data do we really need to start looking at before we can start taking insights, and what kinds of models do we need to develop. But suffice to say that this problem of huge data can be tackled in more than one way. So I mentioned that you can push computing to the data, but you can also start using some fairly cool mathematical techniques like sparsity, etc., to sense the exact amount of data you need to sense to get to the insights that are hidden in there. And finally, the development of algorithms itself is progressing, but a lot of times when mathematicians look at these algorithms and start trying to mine insights, what they miss is that some of this data is physical data. For instance, in a smart city, if you were to have water systems that are developing leaks, and you want to identify the source of the leak very quickly, you need to have deep physical models that tell you what's happening to the flow of water, where the pressure drop is happening, etc. And these physical models, there is no substitute to these physical models. You can't really use mathematical or statistical techniques to get to this information. So in the development of these algorithms, there's both a statistical and a machine learning nature, as well as a physical physics-based modeling that have to come together for us to develop these next generation of algorithms. And this will eventually enable us to act and to have the right kinds of actuators, etc., to take advantage of the information that we're learning. So I'm going to spend a couple of minutes on the last slide here, which kind of summarizes what I talked about. So first of all, I spent a few minutes talking about how computing is now everywhere and in everything. The very fact that sensors went from very few transistors to hundreds of transistors to millions of transistors, and the fact that we have an explosion of this computing all around us. Secondly, even with all this computing, what's changed is that the ability of people to start producing data is adding to the amount of data that's being generated. And there are a number of natural interfaces that are enabling people to access computing in much better ways. So to tackle all of this amount of information, what our argument is that beyond a couple of techniques I mentioned, which is pushing data to the edge, sampling the amount of data that you have, we really need to start pushing the paradigm on computing itself. I didn't spend too much time talking about this, but predominantly computing today follows the so-called von Neumann paradigm, which is there's a distinct separation between memory and processing, and all computing today has this separation. But the way people think and the way intelligence in nature works is that there's much more finely intertwined connections between what memory is and what processing is. And computing itself is moving towards embracing these so-called non-von Neumann architectures that are more finely modeled on the human brain. And ultimately, it's this ability of computing to be modeled itself on the human brain that will enable us to make rapid advances in fields like natural language processing, where computers can understand all the information that humans generate, things like natural speech and things like text-generated data, new data that we've never seen before. The ability of people to naturally look at some new situation and to grab an insight from it. All of these things are very difficult for computers to do today. But if we start making advances in these non-von Neumann paradigms that are bio-inspired or things like quantum computing, we'll get to a point very quickly in the next 10 to 15 years where computers can really get to the information that's hidden in all the data that we're producing today. So with that, I'll end my talk. Thank you.
Okay.